Okay. Today we are honored to have Bill Dudley as our keynote speaker. So I would define Bill Dudley keynotes as the yardstick by which we measure advances in high-performance computing and high-performance networks. Which means that every few years you go and listen to Bill a keynote, you know where we are in terms of state of it. So this is Bill bio taken from the web page. Obviously, if we have to go through this, there wouldn't be any keynote because there are so many achievements, and it will take probably the full hour or more. So today I'm going to give a very short but very personal introduction of Bill Dudley. So this introduction is as follows. Believe it or not, Bill, you changed my life. So I was a graduate student, and I stumbled in some lecture notes on a summer school for students that you gave, I believe, in Canada, in Banff at the end of the 80s, okay? So this was early 90s for me. And then I came into your notes, and I had this crystal clear definition of what a network is. The network is a topology, is routing, and is a flow control. And guess what? The most important thing is flow control. It's not exactly the topology and the routing, okay? Spoiler alert. And then when I saw this, I said, who is this William J. Dudley? This guy is amazing. And then I went into this thing. And I discovered the virtual channels, okay? And then I went into some of your papers. I mean, I read this paper, I'm not kidding you, maybe 10 or 15 times, okay? And so the short story is that the Bill Dudley that we know today is not a coincidence, okay? So it was already there, it just bloomed over there. And without further ado, I think I can let him with the keynote speaker.
Okay, so let me share my screen. Thank you, Fabrizio. That was definitely a blast from the past. I don't think I've looked at my PhD thesis in several decades. But you know, it's interesting, you know, how many things stay the same and how many things change. You know, I wrote my first paper on interconnection networks in the 1970s, and then I worked at Caltech, you know, with Trek sites on the Cosmic Cube. And after we had the Cosmic Cube working, I was not happy with, you know, I was writing programs where I was not happy with the performance of the interconnect. And so, you know, spent a lot of time thinking what an ideal interconnect would be, both in terms of topology and in terms of flow control. And that's where the virtual channels and the move to low dimensional torus topologies came about. So the real focus then was on running scientific applications. We wanted to run big numerical simulations of physical processes. And many things are the same today, but the problem is different. What we really want to do today is run AI, because AI is everywhere. We see it revolutionizing all sorts of life. It's already taking a big role in education. I can see very quickly that we're going to have individual AI tutors for every student that knows how to motivate them, understands how they learn, and can tailor the delivery of material to basically both motivate them and to how they can best absorb it. It's already making a huge impact in medicine, both in analyzing images of all sorts, as well as in mining lots of data to do diagnoses. All forms of entertainment are using AI in one form or another. Things like AI Copilot is already giving a 1.5x improvement in productivity for programmers, and I expect that will get much larger. And in chip design, we are already applying AI. The little cartoon I have here is for a program we have called Prefix RL that designs optimum carry chains by viewing it almost as a video game, where you stick in the look ahead element, the little green dot on the bottom right. And it has done carry chains that beat any human design, and they're bizarre designs. Humans would not come up with them. And so AI is everywhere. And it's really kind of fun being a hardware designer, because AI has been enabled by hardware, and in particular by GPUs. There are three ingredients that make AI work. There are algorithms that I sort of have illustrated by the, I don't even see the mouse, is illustrated by the AlexNet graph on the right here. These algorithms, for the most part, have been around since the 1980s. Deep neural networks, convolutional neural networks, and training them with backpropagation and stochastic gradient descent have all been around since the 1980s. So it takes algorithms, it takes data, large amounts of data, labeled or unlabeled. And then the third ingredient is compute. And it wasn't until we had enough compute that we could train a large enough model and a large enough data set in a reasonable amount of time that the AI revolution really took off, on the order of 10 years ago. Now that we have that compute, you could say that was back in 2012 with AlexNet, the growth has been phenomenal. During the time that people were doing largely ConvNets for images, those grew by about 2 orders of magnitude in the demand, the petaflop days of training, over about a 3-year period. Now that we're in the large language model regime, we see 3 orders of magnitude over a 3-year period. And the little dot in the upper right here is where I estimate GPT-4 is. 10 to the 6 petaflop days. You can think of that as 1,000 exaflop days, 1,000 days on an exaflop machine to train GPT-4 in 2023. How does the AI world differ from the HPC world? Well, people care about it if care is defined by money. The market for AI training and inference is expected to be $300 billion in 2026, whereas the supercomputer segment of the HPC market might hit 10 billion that year if we're lucky. So it's 30 times larger. It's dominated by low precision. FP16 and lower. We're really using mostly FP8 now, and I'm hoping that if we're very clever, we can even drive it down below that. As opposed to typically FP64, the dominant operation is a matrix multiply, and when you look at how it's used in these applications, it's limited by both compute and communication. It's interesting that there is an export restriction on our A100 and H100 parts now. We cannot ship them to China, but we can ship the A800 and H800 that have 1/3 of the communication bandwidth to stay under the needs of some of these most demanding AI applications. And also the applications have very well understood persistent traffic patterns. In contrast, most HPC applications are actually memory bandwidth limited. It's too bad that everybody runs a high performance LINPACK benchmark, because it's not. But the applications that people really care about, in hydrodynamics and radiation transport, in climate modeling, are all memory bandwidth limited and wind up using a tiny fraction of the compute because they're just saturating the memory. And also because they're saturating the memory, they're typically not communication limited. So they're not actually stressing the network that much, which doesn't give us a hard enough problem as network designers. But on the AI side, it is communication limited, and we understand the traffic pattern. It's a large and growing market, so we can specialize the network for the needs of AI. So what does AI need from the network? And so you have to look at how we get parallelism out of an AI application. For as long as you can, you want to do what's called data parallelism, because it's very simple. You simply create 2 copies of the AI model you're running, and you basically take your data set and you run part of the data set on one copy, part of the data set on the other copy, and they exchange parameters, they exchange the gradients. I'll have a little more detail on that in another slide. There are some times where you can't do that. So for example, just to hold the parameters of GPT-4 takes over 20 GPUs just to fit in the memory. And so there you have to break the model up and run part of the model on one device and part of the model on the other device. There are kind of 2 ways you can slice this. If you slice the model horizontally, you're basically taking individual matrices and basically decomposing those matrices so that part of the matrix is on one GPU and part of the matrix is on another GPU. If you slice this model vertically, you're basically taking different layers of the network and putting them on one GPU and others on the other GPU, and that's called pipeline parallelism versus tensor parallelism. And so if you combine all 3 of these, the pipeline parallelism and tensor parallelism together are called model parallelism, because you're parallelizing the model, and then the data parallelism is you're parallelizing over the data set that you're training on. And if you combine all 3 of these, you basically get the most parallelism, and you need that to train these large language models. You need to run on clusters of thousands to tens of thousands of GPUs. And it takes 20 GPUs just to hold one copy of the GPT-4 model. You'll then have 100 of those copies for 2,000 GPU training regime. So let's start with data parallelism. So each individual GPU and data parallelism runs the whole model. It takes a batch of training data, whether it's images or whether it's tokens, if you're doing large language models, and you do the forward and backward pass over that batch, and you compute a set of gradients, which are the changes that you're going to apply to the parameters. And then you want to apply those changes not just to your parameters, but if you've got 1,000 GPUs all running 1,000 different batches, you're going to I should say subsets of that batch. You want to combine those gradients and apply them all of the parameters at once. So if you had a batch of 256 images and you ran it over 128 GPUs, you'd be running 2 images on each GPU. We usually run much larger batches over even larger numbers of GPUs. But the operation here that you want your network to be really good at is all reduce, right? Everybody is basically adding a bunch of numbers, into this set of parameters. And so you want to basically take those, do the all reduce for each parameter, and then and then distribute them to everybody. For model parallelism, there are a couple ways. If you're doing the tensor parallelism, there are a couple ways you can slice the tensor. You can split X column wise and A row wise, or you can split, slide jumped too fast. You can split A column wise and X row wise. And you really want to do the latter, because if you do it this way, you wind up having to do an add, synchronize, make sure these are both done, and then do the add, and then do the JELU, where if that's a nonlinear operation. If you do it the other way, it's completely independent. You can actually do these 2 JELUs and you just output the data. There's no synchronization, no global add that's required. So if you look at what you do need out of the network here, on the forward pass, you need to take this input X and basically copy it to both sides. So this is basically a broadcast. And on the output, it's all reduced. And remember, you're typically not just doing it 2 ways. You're typically doing it 10 or 100 ways. So it's a big broadcast and a big all reduce. And then on the back propagation, it's exactly reversed. You wind up doing a broadcast with G and an all reduce with F. The other place you see a lot of communication in neural networks is in recommender systems. And the communication there is a need to access these large embedding tables. It's not unusual to have recommenders where the aggregate embedding tables are terabytes. And they don't fit on one GPU or even one CPU node. And so you wind up having a communication of taking the words you're trying to look up and running and accessing the embedding tables for them. There's often a reduction within the embedding table and then a communication back. So how do we meet this need today? So today at NVIDIA, we offer something called a DGX SuperPOD. So let me walk you through a SuperPOD, starting at the individual component and working upward. So the individual GPU is a Hopper H100. The GPU chip itself is this little rectangle in the middle. These 6 darker rectangles around it are stacks of HBM3 memory. There's an aggregate 94 gigabytes of HBM3 memory with 3.4 terabytes per second of bandwidth into the GPU. It's an enormous amount of bandwidth. Everybody always thinks these things around on the SXM module are memory chips. These are inductors delivering the power to this thing. And 700 watts at about 0.7 volts is a kiloamp of power, and doing that efficiently is actually quite a challenging technical problem. There's a lot of neat features on the H100, like the transformer engine to facilitate the use of reduced precision in running modern transformer models. We actually have dynamic programming instructions for bioinformatics, but for the purpose of this discussion on networking, those aren't particularly relevant. The way to think about this is it's a component of our system that delivers 4 petaflops of sparse FP8 performance and 900 gigabytes per second of external bandwidth. That's the bandwidth of the NVLinks coming out of this card at 700 watts. So the next step up in building the DGX SuperPOD is we take 8 of these, stacked here on the board, and we put them in a system along with 4, 3rd generation NV switches. And each of these, GPUs has, 18 NVLink channels coming out of it. They're spread across, 5 and 4, 5 and 4 across the NV switches, and then those are connected to the back panel, so that there are actually 18 NVLinks that come out of the back panel. And so it's one way to think about it, it's an 8-to-1 taper at this level from the bandwidth you have within these 8 GPUs and the next level of your network hierarchy. this is the wiring diagram, and the main reason I'm showing you this is just to show that there are two separate networks here. The H100s are the GPUs here, and the NV links on the H100s connect down to the NV switches. Each of these is 4 and 5, 4 and 5 going across, so that each H100 can have full bandwidth, all 18 of its links talking to any of the other H100s within its cluster. And if you excluded everybody else, it could actually get all the bandwidth out the back panel as well. But there is an 8-to-1 taper at these NV switches. And that goes to the 18 OSFP connections for NV link out the back panel. And then the PCI connections out of the GPU go to ConnectX 7 NICs via PCIe switch. And those then connect to 4 OSFP connectors, 2 CX7s on each OSFP, to build the InfiniBand network. So there's two separate networks here. We tend to think of this as the NV link network as the scale-up network, and the InfiniBand network as the scale-out network. Both of these networks support sharp acceleration. The NV link sharp acceleration is such that we wind up basically taking the N reads that we would have to do with the read and reduce on A100 and an H100 with sharp. It's basically one read. We basically do N reads to send the partials. The switch does the sum, and then we read the result that we want. The broadcast result works in kind of a similar way. We have to do only one write, and then we get N writes out of the NV switch. And this is basically it's a 2x for the all reduces, which are a huge part of the deep learning workload. This is the 2x reduction in demand, or the way to think about it is 2x increase in the effective bandwidth we have. So we take those same NV switches that we used in the SuperPOD, and we put 2 of them in a pizza box, and that basically is the next level of interconnect for the NV link, the scale up network. It winds up having 128 ports coming out the front, with there's a spread across the 32 OSFP cages, and enormous amount of 6.4 terabytes per second of bandwidth. And that lets you build up and out depending on how you want to do it. Each of the boxes here is 8 GPUs, the DGX box. You have 40 per rack, and then you can either connect those up with NV links up to 256 GPUs, 32 of those boxes, or InfiniBand up to tens of thousands. And the InfiniBand director switches are sort of shown here in the middle of this particular configuration. And there's some real reasons to want to do this on the NV link side. From the programming system point of view, the NV link network is a load store network. So I can, on a given GPU, once you've set the memory maps up, I can do a load or store operation into the memory of any GPU on the NV link network. And that just simplifies programming compared to having to marshal your data into message buffers and make the MPI calls and everything else you have to do over on the InfiniBand side. But there's also just a lot more bandwidth here. And by section bandwidth, there's 9 times as much bandwidth on the NV link network, and 4.5 times as much reduction bandwidth. So whether it's on HPC applications, AI inference, running up to 30x speed ups, or AI training up to 10x speed ups, there's big advantages to that communication bandwidth and bisection bandwidth turn into. For weak scaling, if we increase the size of the model in these large language models, you can start at billion parameters and run up to a trillion parameters. Across that range, we get perfectly linear speed up as we increase the model size and increase the number of GPUs. What's more impressive is we also get very close to linear strong scaling. If we hold the model size constant, the GPT 375 billion parameter model, and we scale it from 64 GPUs to 2K GPUs, it's nearly linear speed up. And that is a testament to the very low overhead of scaling on these. So just to sum up, the current state of affairs with the DGX SuperPOD is that we have these wonderful GPUs, the H100s, each of which has 18 NV link ports coming out of it. The DGX box takes 8 of those and 4 switches and does an 8-to-1 reduction, you can then hook up to 32 of those together to make a 256 GPU that looks like a big GPU. And if you are willing to pay for the switches, you can hold that 8-to-1 taper so that the bisection width is 1/8 of the aggregate bandwidth out of the GPUs. Above that, you hook it up with InfiniBand switches and the InfiniBand network, and you can scale up to tens of thousands of GPUs. The demands of the large language models require that. We see many customers training on tens of thousands of GPUs, and many of the problems you have with the large scientific computer having to do checkpoint restart and the like happen at that scale as well. In fact, many of these machines would be number one on the top 500 list if people would take them away from the profit-making operations that they're doing long enough to run HPL on them. So that's where we are today. And I should say one thing about the DGX SuperPOD is that compared to sort of trying to acquire the components of the system and put it together and bring it up, which is the way most large supercomputing acquisitions are done, everything is pre-configured for the DGX SuperPOD. So if you buy DGX SuperPOD, you buy the DGX boxes and the NVLink switches and the InfiniBand switches, and you plug it together, it just works. All the software is already done. It's been debugged, and the bring up is a day and not a number of months. So in terms of looking forward, let's start with the physical layer, and I'll start with a cartoon of how one of these systems looks to the logic designer. So on the chip, we've got a bunch of logic that talks to other logic over 2mm links. We've got our links on the interposer out to the DRAM that talks over very short links as well, and that's one GPU, and then we may have multiple GPUs like in the DGX box that's on a printed circuit board where the connections are now 30 to 50 centimeters, going tens of terabits per second, which is a big reduction in bandwidth, I'll point out, compared to what you had on the GPU. And the current electrical interconnect here is around 5 picojoules per bit. When we need to go board to board, we're now going 1 to 3 meters. We've had another reduction in bandwidth, and we're still electrical at about 5 picojoules per bit. We tend to go optical on these cabinet-to-cabinet links. They're 5 to 100 meters, which is too far for an electrical link unless you repeat it every meter or so. And the power is up, but more importantly, the cost goes way up here. The electrical links cost 10 times as much per unit bandwidth these days as the electrical links. And this is worrisome to us because the electrical links aren't getting a whole lot better with time. The chart on the left here shows that the transistors, while you get more of them as you move from, say, from the 16 nanometer node down to the 5 nanometer node, they're not getting faster. I mean, the fan out of 4 inverter delay has been stuck at about 10 picoseconds, since the 16 nanometer technology that we used way back on, I don't remember which GPU that is, Pascal or something was probably our first 16 nanometer GPU. And then what's also more worrisome is that as we push our electrical links, we now have electrical links going 200 gigabits per second per pair, the reach gets reduced, right? We could go 2 meters when it was 100 gig. We can now only go 1 meter at 200 gig. And so it means that we have to jump over to optical signaling earlier. It also puts a big amount of pressure on us to put a lot of GPUs close together so we can connect them electrically. And some customers kind of push back on this because we tell them, we want to build a 200 kilowatt rack, right? And that's, look at the big supercomputers. That's what Frontier is. And if you build a 200 to 300 kilowatt rack, you jam a lot of GPUs into a small space, you can connect them all electrically. You can get to that 256 node NVLink network electrically. But the person just needs to provide you with cold water right at that rack and liquid cool the thing. That's pushing back against sort of a data center culture where people like 30 kilowatt racks and they think 40 is a stretch. Actually, some of them like even less than 30. Anyway, if you look at the physical layer, the figures of merit are power, cost, density, and reach. And then if you sort of bring all the students into the classroom, you give them the test and you get the report card, this is what it looks like. And the real thing to do here is to compare the electrical cable to the active optical cable. And what you see is that power is about the same, and a little bit more expensive for the AOC and not that much. The big issue here is the cost. The density is better on the active optical cable and the reach is way better. But to get that density and reach, you got to pay 10x as much per gigabit per second. And we have to find some way of dealing with that. And so one thing we're very excited about is co-packaged optics using dense wavelength division multiplexing, because our estimate is that if it's successful, it will be even denser than the current active optical cables at a cost, this may be a little bit optimistic, but within a factor of 2 of electrical signaling, and a power substantially less than the electrical signaling, and a reach that's the same as the active optical cable. Now, I should point out that when you look at these figures of merit, like especially the ones of power and cost, you have to consider the whole link. I very often, talk to technology providers, and they tell me about this wonderful technology that they have. It's almost no picojoules per bit, but they're only looking at the actual transmitter and receiver. They're not counting, somehow that had an automatic advance. They're not counting, the serialization and deserialization, the clock recovery, and the actual supply lasers. So you have to look at the entire system. And one thing I've found with some of our links is sometimes you wind up with overly enthusiastic designers who over-design the link layer. You have a very reliable physical layer out here that doesn't require enormous amounts of error correction and all sorts of stuff. But they like to overbuild things, and so they'll put you'll have a link that's consuming a tenth of a picojoule per bit, and they'll wind up putting a 2 picojoule per bit link layer in front of, which kind of defeats the whole thing. So let's talk a little bit about optical signaling. A system concept we've been playing with is to deliver switch cards that basically have a GPU switch, like the NVLink switch or one of our InfiniBand switches, with co-packaged optics that basically come out on pigtails, and you can basically connectorize them out to a front panel with a bunch of fiber connectors, fiber ribbon connectors, and a GPU card with one or maybe a couple of GPUs on it, with co-packaged optics for all the NVLinks, bringing those out to a connectorized panel. You would then package these up, so you would have a GPU rack with all these GPU cards and a switch rack somewhere with all these switch cards. And because these are now optical cables, the reach is 100 meters. There's not this huge pressure to build the 200 kilowatt rack. You can spread them out a little bit, although you don't want to do that gratuitously, because latency is badness, right? And if you make these cables long, the latency is going to get larger. What this looks like at the next level is with a laser comb source. We're hoping that quantum dot sources will eventually become widely available, but right now these are usually DFB arrays. That you have a supply fiber that brings the comb into the transmitter chip, and the transmitter chip has a bunch of ring modulators that basically either pass or attenuate each line of the laser comb, and they do that at a moderate modulation rate. And we're playing with things. We're actually looking across the design spectrum from having a few lines with very high modulation rates to lots of lines with lower modulation rates. So modulation rates we're looking at range from like 25 gigabits per second up to 200 gigabits per second. Whatever trade-off you make there, what we want to do is we want to have one extra line compared to the data and forward the clock, because then we don't have to recover the clock on the far side. Here we have a ring modulator we use to pass only a selected line to a receiver, where we have a diode and a transimpedance amplifier that basically converts that signal back to electrical. I think I basically said most of what is on this slide. Now here's sort of a cross-section picture of what that looks like. On the switch chip, it sits on an interposer. On that interposer, then we have a photonic integrated circuit that has the optical components. That is the rings and the waveguides and the couplers, and then we have an electronic integrated circuit that sits on top of that basically takes the very short reach link from the switch and drives the modulators for the rings, and basically has the transimpedance amplifiers and serializers and deserializers on the receive side. Essentially, the same thing happens on the co-packaged GPU. It'll be the same EIC and the same PIC, but just a single GPU driving it rather than having a switch, which will have way more bandwidth coming out of it. The power budget we're currently looking at for an early prototype is about 3.5 picojoules per bit, the bulk of which is the laser. I mean, these, and I have to say, this is wall plug power, right? So if you have a 5% efficient laser, you have to put a bunch of picojoules per bit in to get not so many coming out. Then the EIC, that's basically the serializers, deserializers, modulators, and the like, takes about bulk of the power. Yeah, and the optical thing is hugely efficient. Once you have a comb to modulate and the electrical signals to drive those rings, they don't take very much power at all. I think we can actually do better. Right now, we're budgeting 250 femtojoules per bit for this electrical link from the host to the TX and RX, and I think that we're actually going to be much more likely in the 100 femtojoules per bit there. Now the link budget we're playing with, after that 20 to 1 5% efficient laser, we have about 3 dBm coming out of our laser. We lose a bunch at each of these couplers every time we go in and out of a chip, so that we're down to 2.5 going in here. We lose some in the transmit chip, so we're kind of coming out of this transmit chip at -4 dBm, and then in a couple couplers later into the receive chip at almost -7. After we get across the rings, we're at -9, and then at the photodetector input -12, which gives us a 2 dB margin. But we would like a much bigger margin than this, and one reason is we'd like to be able to use these with optical circuit switching, where the insertion loss that optical circuit switch is bigger than 2 dB, right? So we need to be able to tolerate more loss on the link. So we're working on trying to make every part of this a little bit tighter and get a little bit more link margin. One of our first prototypes, we're doing a 400 gigabit per second per fiber, which is 25 gigabits per second per color per polarization, 8 channels, 100 gigahertz channel spacing. We're looking to scale this up to 800 and 1.6 terabits per fiber by doing higher bandwidth and more channels. We built a number of test chips over the past couple of years, starting with the numbers on these are usually the year that we did them. RPC 19 was done in 2019. Testing micro rings, doing different couplers, doing different waveguides, doing different receive architectures, and we're very close to putting out a full link that we hope will have operating in the very near future. So that's a physical layer. What do you do with that physical layer? You build a topology. And it still amazes me that most people build folded Clos topologies that are often called fat trees, but Clos wrote his paper in the 60s and Lyserson wrote his in the 80s. So it's sort of a 20-year credit to Clos. They're just inefficient because they sort of assume the worst case. You have to sort of route up and then route back down instead of going exactly where you want to go. Or the whole idea of a Dragonfly network is, in the good case, you can do one long hop. You only need to ever go across one expensive optical link, assuming you can wire the groups electrically. And as a result of that, using the assumptions that were in the original paper, I'm trying to remember when this came out, 2008. It's $80 per endpoint rather than 160. Those constant numbers have changed, but the ratio hasn't. The reason you get that is that it's a much lower diameter, and you have essentially lower cost for the same bisection bandwidth. The challenge here is it's really easy to route a fat tree. You basically just route obliviously up. You can even route randomly up until you get to a point where you can see your destination, and then you route directly down to that destination. Routing a Dragonfly correctly requires global adaptive routing. There are otherwise traffic patterns that will completely bring it to its knees. And it's also very sensitive to congestion. So you need to have some sort of congestion avoidance mechanism if you're going to use a Dragonfly. Now, one of the classic problems with the Dragonfly is that building them out would require recabling, right? If you had 2 groups and you wired them together, and then you added a 3rd group, now you have to take a 1/3 of the connections from each of these 2 groups and rewire it to that group. This problem goes away with optical circuit switching. It also solves the problem of partitioning the Dragonfly up. If you have multiple users on it, you can now give somebody, if they have 16 groups, give somebody 8 groups, somebody else 4, somebody 2, and so on. And then all of their connections don't have to go through somebody else's group. They can all be directly connected to each other. And you can solve a reliability problem this way by having a spare group and swapping a spare group in, making the group the field replaceable unit. So Dragonflies and optical circuit switches are a really nice combination. So much for topology. Now that we have our Dragonfly, how are we going to route on it? Now, it turns out that you get congestion in two ways. One is you get core congestion, say when every endpoint, every GPU in this group wants to talk to this group. They all try to route minimally. They all want to use this link, and that will congest this one global link. You can also get endpoint congestion. If everybody in this group wants to talk to this one endpoint, they're going to congest the endpoint. And these are two very different problems, right? The problem on the left of having one group all going to another group has to be solved by routing. It requires global adaptive routing to spread the load over the global links by routing some of them non-minimally. The problem on the right of endpoint congestion requires source throttling, right? There's no way of getting more over this endpoint than what its bandwidth is, right? And if you're trying to send 3 times that much bandwidth, it's going to all back up and cause tree saturation. So let's talk about the global adaptive routing problem first. So say everybody in this group, the orange group here, wants to talk to everybody in the green group. The simple solution is one of them takes this link, he gets to go minimally, and then one of them goes to the red group, and one of them goes to the blue group, and they take the hop from the red group and the blue group to the green group. But doing this requires making a decision to route non-minimally. And it turns out there's very good ways to do that, that ultimately all spring from Arjun Singh's work on his PhD thesis of global adaptive routing. And the key of global adaptive routing is it's not the usual the original adaptive routing where people would sort of opportunistically, go to a switch and make a local decision to take an idle output port. It's a global decision here where you're choosing between routing minimally, as the one on the right did here, or routing non-minimally, as the other two did. And when you route non-minimally, then what you're really doing is you're basically reverting to Valiant's algorithm for the global part of your route by randomly picking a group to route through. And there are good ways of doing this, and it can be done in a very successful manner. At this point, I would say it's known technology. Then we get to the issue of flow control, and I tend to agree with Fabrizio. I think all of these aspects, the topology, the routing, and the flow control are all important, but the flow control is often what really determines what fraction of your network you really get to use. And we'd like that fraction to be close to 100%. For a lot of networks, unfortunately, it's like 30 or 40%. So here are some thoughts on flow control. So the first thought is, and this sort of relates to, there's coupling between all those elements, coupling between routing and flow control. I may have a single GPU with 18 NV links coming out of it, and I want to send one really big flow, and I don't want to serialize it over one of those 18 NV links. I want to use all 18 NV links. So even right coming out of the GPU, I cannot run a flow all over the same path. That is not a realistic thing to do. So if I'm going to be running a big flow over 18 things coming out of here, they're going to be going different ways, right? When they get to the first switch, they may choose to go in different routes, and they're already on different channels. So you're not going to keep ordering by trying to force everything on one route. So, a single flow can use all outgoing links, can use lots of routes through here. You need to reorder at the far end. One thing that you want to do to keep the reorder buffers small is keep the worst case latency low. And a very simple way of keeping the worst case latency low is to have a very short time to wait. That's like time to live, but you don't count the productive time. If you're actually moving through a switch or over a link, that doesn't count. What counts is the time you spend waiting. And if you wait 500 nanoseconds, something's wrong, drop the packet. And I'll explain a little bit later under congestion control how we avoid just dropping every packet under these circumstances. And another thing to realize is I've got 18 links coming out of this GPU. That's a horrible thing to waste. That's the first level of my switch. That should be an 18-way switch. And that should be enough to connect up perhaps a reasonable sized Dragonfly group, where then the switches out of that can take that 18-way expansion and expand it further to get to an even larger reach. When you start looking at what you need in terms of buffers, it really has to do with two delays. You need a buffer at the source to handle retransmits, right? So if I do drop the packet, I got to have the packet back here so I can send it again when I get the NAC that says I dropped it, or timeout. The NAC tends to be a little more efficient, and I need a comparable size buffer at the receiving end to reorder. If one packet gets through and then another packet of the same message gets dropped, I need to wait until that it comes in so they can be received in order. And these are going to be based on, say I have a 200 gigabit per second link, that link times the end-to-end round trip time, if I call ER here for end-to-end round trip, which we'd like to bound at like 4 microseconds. That's not much. That's 100 kilobytes for each link. So that's an amount of SRAM much smaller than the PHY for the links. That's a reasonable number. The other buffer that I have is link buffer, and the link buffer should not be big. All that does is delay your discovering that you have a problem, because people are accepting your packets and just stuffing them in the buffer. If the packet blocks, there's no point in delaying your knowledge that you've run into some problem. So here it's going to be the round trip time over a fiber, which is about 100 nanoseconds. So these are even smaller buffers. And so even if you have a switch with a lot of bandwidth, say 128 of these 200 gigabit per second links, it's still a tiny amount of SRAM that you really need in buffering in the switch. So the key here is basically to make the expected case that you fly over links and through switches and never wait for anything. And you do this by dropping packets as soon as they start waiting very long. Now, how do you get around not dropping all your packets? And that really falls into the heading of congestion avoidance. And this is, remember, the case when all of these guys want to send here, right? If you just let them do that, and they wind up saturating, even if they globally adaptively route, saying, oh, we're all going to the same group, let's go different ways, they're going to get here and it's going to back up. And because you can't deliver that, it's then going to back up, to the network, this phenomenon called tree saturation, and slow down everything in the network. Now, the traditional way people have dealt with congestion avoidance has been things like ECN, where you wait till it happens, and then you tell people, oh, you've congested the network, please slow down. And you have some kind of, ramp down on the source nodes that are causing the congestion. And then when the congestion is relieved, they have some way of ramping their production back up. The problem with that is you've already done a lot of damage. So what's much better is to use a reservation protocol, right? Where to avoid congesting the network, you would basically say, okay, I want to use this endpoint. I'm going to send that endpoint a request for reservation, and then he'll say, okay, here's your reservation. It's just like going to a restaurant, right? If you make a reservation for a table, you get there, you sit down, you don't wait. If they can't take you at 6, they'll say, I can take you at 7. You don't bother leaving your house until 5 minutes before 7, so you get there at 7. Your packet should be doing the same thing. Now, the thing you might point out is that, gee, I have to send a message to the destination. Might as well piggyback some data on that. And so the thing that Ted Jang came up with in his PhD thesis was the speculative reservation protocol, where you basically send the packet speculatively. And so the dotted line here is a speculative packet. And if he gets to the destination, he basically, you're done. But if he gets close there and his time to wait runs out and you drop the packet, a NAC gets sent back, but a forward header continues on and actually sends the reservation back to the source. And this way, if you get lucky to get through the network, you actually have piggybacked some data on the request for reservation. If you get blocked in the middle, that NAC comes back, and then you wait until your reserve time, and then you're guaranteed to be received because you haven't oversubscribed the output bandwidth at that point in time. Since this paper was published in 2012, there have been a couple other similar protocols published that are essentially based on reservations. And if you use a reservation protocol, whether it's speculative or not, I mean, what the speculative protocol buys you is, in the case when the network is not loaded, you don't have to pay 2 round trips to get there. One round trip to get the reservation, and another one way to deliver the packet, and the remainder of that round trip for the ACK. Now, the real problem is, remember, is usually an oversaturated link into a destination. And if you have networks with very fine-grained transactions, what you really want to do is take advantage of the fact that the last hop before that link is where you want to make the reservation. So if you're going to be dropping that speculative packet, you're going to be doing it at the last hop switched. And if you do so, then that last hop switch makes the reservation for you, rather than having to go all the way to the destination to get that reservation. So here's some experimental data on how this works in practice. This is an experiment where we're running uniform traffic, and then we're running a hotspot of aggressors overloading some hotspots by 5x, starting at 2 × 10⁴ cycles into the simulation. And what you see is with no congestion control, your throughput drops to an abysmal amount of, this is sort of the innocent bystander traffic, getting cut to 1/4 of its original bandwidth. Your latency goes off scale. So everybody who's suffering here is sitting in a very long line, and things are very bad, and it doesn't recover. With ECN, one of these things where you wait for the congestion to happen and then you recover, you see that your latencies are going way up, and you say, I have congestion. Let's tell these misbehaving guys who are oversubscribing the hotspots to slow down. And you do, and they recover, but it takes, 40,000, 50,000 cycles for that recovery to happen. Actually, it's more like 100,000 cycles before the latency comes back down. And that's not really tolerable, in these deep learning environments where it's the tail latency you worry about. You worry about the latency of that last packet because there's synchronization going on here. Everybody else is waiting for him to show up. If you're using the last hop reservation protocol, it's not entirely a non-event. I mean, your average latency goes up, and that's because some people are waiting to deliver to those 5x oversubscribed nodes, but your overall throughput doesn't budge. You're not hurting the innocent bystander traffic at all. It's just getting through as if there was no other thing, because you're not tree saturating the network, discovering that, and then throttling back. So I'm just about out of time, so let me wrap up here. AI is everywhere. It's transforming all aspects of our life. It's a very exciting time technically to see all the great applications. This has been enabled by GPUs, and it's currently being gated by GPUs. There's huge demand. People would like to build even larger language models. They'd like to do all sorts of exciting stuff with AI, but they're limited. The GPUs are only getting so much faster each generation, and very little of that, by the way, is coming from process technology. We're having to build larger and larger clusters to meet that growth in demand. One way we can get a little bit more performance, although it's a one-time card, is to try to specialize our networks for AI. And to do this, we need to look at how these AI models are parallelized and specialized for that. So, for model parallelism, it's all reduced, right? You basically compute some parameter gradients, and you want to share those parameter gradients with every other copy of the model. That's an easy one. For tensor parallelism, it's broadcast and all reduce. And then there's something called sequence parallelism that I really didn't have time to go into, but it really demands a gather scatter, which puts real demands on the network if you're not doing it right. Today, we have a pretty effective solution for AI. And in fact, we have a lot of customers who can basically just order a DGX SuperPOD off the shelf and build machines up to tens of thousands using InfiniBand, where the first sort of 256 are clusters of NVLink networks. And it's particularly effective to do sort of model parallelism within those NVLink networks where the communication demands are higher, and then do some reduction of bandwidth request before you go out over the InfiniBand, where the bandwidth tends to be more expensive. And on both the NVLink and the InfiniBand networks, we have sharp collectives. And so things like all reduce essentially double our effective bandwidth. So I gave you some of a glimpse of the future, and these are a bunch of things we're working on in NVIDIA research. I should add this disclaimer that this talk is my own opinion and does not reflect the opinion of NVIDIA or any future NVIDIA product plans. I'm personally very excited about co-packaged optics. We have a big project in NV research to do DWDM co-packaged optics, and can really change that equation, that bad report card we have for optics right now, which is mostly bad in the cost column. We're hoping we can really, drive both the cost and the power of optical interconnect quite a bit down by integrating it. If you do global adaptive routing, you wind up enabling topologies like the Dragonfly, that essentially give you 2x cost performance, twice the performance for the same cost. But doing so requires, kind of being clever and making a decision for each packet about when it's time to route globally, basically to route non-minimally to a far group rather than going to the group that's your actual destination. I see a lot of networks today where the worst case packet delay is quite large. I mean, for Ethernet networks, it can get into the milliseconds. And to me, this is a failure of flow control, and you really don't want that. You want, an agile network where a packet either gets to a destination or you drop it and ask for a reservation. You should never have a packet waiting even, a microsecond in the network. There's no point to that. You should either have the bandwidth reserved or don't send the packet. Sending lots of packets and having them pile up in the middle of the network is a really clumsy way of allocating bandwidth. And the way to do that is to do a reservation-based congestion avoidance, where if your packet can't get through almost immediately, you send it to that last hop, and that last hop sends you it makes a reservation for you, reserves a certain amount of bandwidth for you at a point in time, and tells you when to try again. And then when you try again, you will get right through. So I think the future for networking is really bright. AI has created a huge demand, and a huge demand with very well understood patterns that can benefit from a certain amount of network specialization. So with that, I guess I have 5 minutes left. If people have any questions, let me stop sharing.
Bill, there are some questions in the Slack channel. I don't know whether you do have access.
I'm not on the Slack channel. I was hoping they'd put them in the Slack. Oh, it says HOTI Slack link. If I click on this resources thing, do I get that?
Yeah, or I can read them for you. I mean, obviously.
Sure. Why don't you read them?
Okay. First of all, we have a question for CC. ICC1. CC is asking about the similarity between AI ML training and inference and blockchain mining and 5G wireless, that they all rely heavily on gems. Okay, so that's the first.
That's an interesting question. I didn't think blockchain mining relied on gems. There's a particular cryptographic calculation that it's doing, but from the networking perspective, I think the AI training is the real heavy network user. The inference tends to run mostly on one GPU, although the big models now, like a single copy of GPT-4 doesn't fit on one GPU. But even then, the communication demands are a lot lower than for training.
Okay. Then there is another question from Harsha Chenji, and he's asking you whether you have considered hollow core optic fibers for higher speed of light in vacuum, thus lower propagation delay.
Oh, that's an interesting question, right? So instead of getting an index of 4 or whatever and running at √2 speed of light, or half the speed of light, I could run at the speed of light. We haven't looked at it. It's an interesting idea. I'll have to talk to my optical people about that.
Yeah. A question from Sayan, which by the way I can only subscribe, is asking about he called these graph-based topologies. What is your opinion of the practicality of graph-based topologies like jellyfish, or that it can offer higher path diversity than Dragonfly? I mean, the way I would recast this question is that you're interested in ultra low diameter networks, right? So diameter.
Yeah, so I have to confess, I probably need to keep up with the literature a little bit more, because I have not heard of what a jellyfish is other than something in the ocean that stings you. But I'm always looking for.
It is the same for networking. It's a bunch of connection randomly between nodes.
Okay, I'll have to look that one up. I'm always looking for better ideas and trying to feed them into our product people. So I will try to find that reference and understand it. But I don't know what it is right now.
Yeah. Theodore has another question. For CPU compact optic channel bandwidth, do you see go beyond the 50 gigabit per second NRZ to PAM4, or will it stay NRZ?
Oh, that's a really good question. So it's an optimization, and we've been trying to look at the trade space there about whether to push. And actually, it's a sort of a three-dimensional trade space, because it's what is your baud rate? How many levels do you have per color, and how many colors do you have? And there's a sweet spot on the electronics keeping the baud rate under 50. 50 or under, because 50 or under, you can use some very simple serializers and deserializers that give you a very low energy per bit in the electronics. And that's true of whether you're driving NRZ or PAM4. And so you like to keep relatively slow to keep the clocking logic in the electronics low power. And then the question is, do you drive more levels, which has some noise and link margin implications, or do you stick NRZ and run more colors? And I think the answer there's not obvious, but I think you do want to stay relatively low bandwidth to keep the electronics low power.
Yeah. There is a question from Navneet Rao, and it relates to your Dragonfly OCS design that you presented before, I believe, and is asking whether you are able to characterize flows like elephant versus mouse flows on OCS. What is your point of view on that?
Yeah, we haven't looked at that very much. We've looked at using the OCS mostly for incremental build outs. You don't have to pull cables when you add another group, and for field replacement of a group that has a bad GPU. So you can take that group down, replace the GPU, and then bring it back up. In a lot of these applications, it isn't really flows the way traditional networking is. It's you're exchanging parameters, and it's one collective operation, an all reduce or something like that. And so in the sense of each phase of the deep learning algorithm is something like you're doing an all reduced, you're doing a broadcast. It's not a flow from a single port to another port somewhere.
Yeah, and I think there are other questions, but we are at the end of the hour. And obviously, this is a talk that gives goosebumps to a network designer, in particular the second half of the talk. So you relate to all these problematic and these discussions and these. Okay. So well, let's give Bill a big round of virtual applause. So it's a pleasure to have you at Interconnects once again.
Okay. Well, thank you very much. I actually have to run to the airport, and I hope I run into you guys in person one of these days. Bye.
Absolutely. Thank you, Bill.